Dear students, today we will discuss about the machine learning, chapter number 6, which is related to the support vector machine. So, support vector machine is a very old technique, but still it is used to make a separation between two classes. So, this is very interesting algorithm of machine learning. And here we use the hyperline for this one, and we also use some mathematics. I think if you go through your subject of operation research, there is a equations which are used for the support vector machine, and that is called objective function. Objective function defines your line, whether it's a straight line, diagonal, curvy, and then apart from that one, in the support vector machine, what do you think? You have like some constraint, then how your support vector machine or support vector line will be appearing, whether it's in a straight line or a circular line, so that the limitation or the restrictions will let you know about it. So let's see, dig deep into the support vector machine, and we hope that we can learn about it, right? So this is a support vector machine. Yeah. So it is more related to statistical learning theory. It was first introduced 1992, so it's a quite old subject, but still people are using it. SVM becomes popular because of its success in handwritten digital recognition as well. 1.1% test error rate for the SVM. This is the same as the error rate for carefully when we construct some like ANN artificial neural network or LeNet4. And SVM is like, regarded as a very important example for kernel methods, one of the key area in the machine learning. And these are some references for you to study. So this was the hyperline which I was talking about, that it classify your two classes, class A, class B. Like for example, if you want to classify dogs and cats, so in the two classes, if you want to classify those who living in the on the rent and those who living in their own houses, or if you want to classify different brands of cars. So this is like, in the variety of structure it will be used. So consider a two-class linearly separable classification problem. Many decision boundaries. The perceptron algorithm can be used to find such a boundary. Different algorithms have been like, proposed, and all decision boundaries equally good or not. So we have to see that which boundaries are perfect and which are not perfect. So this line, as I told you, this line is not a fixed one. It moves like, toward the x-axis and towards the y-axis. So when it moves toward the y-axis, the angle becomes more, and when it moves towards the x-axis, the angle becomes smaller. And we have, this is a diagrammatically a diagram. We have it for x, and we have a function alpha, and then we get a y value. So sometime we can represent in a sine of w dot x plus b, and we can have the function of x, w, and b. So we have three parameters over here, x, w, and b, and then we get a function out of that one. Example of bad decision boundaries, like, yeah, so in this one, some decisions could be like, good, some could be like, bad decision boundaries, and we see that where should be the hyperline. Sometimes our hyperlines are not like, marked up to the in a proper way, like in class. And if you see on the left hand side, there is a more spaces you can see in the class B, and on the in the second one we have more spaces in the class A. So we need a line which is like, like in equidistances, or in a way that it does not like, interrupt each other or interrupt the class of each other. So it's basically it's margin of a linear classifier as the width that boundaries could be increased by before hitting a data point. And then you can see the maximum margin linear classifier, like basically it's a linear classifier with the maximum margin. So the margin is basically the width between class A data points and class B data points. So that is basically the margin basically. So the maximum is the margin, the better it is. So this is the simplest kind of SVM, and we call as a linear SVM or LSVM. So here you can see support vectors. Yeah. So these are the data points that the margin push up against, right? So these two are, you can see this have been highlighted, two white data points and one dark data point. So these three are called like data points which like push each other to make a margin. Okay, so why we need a maximum margin? Because it's better to have a clear distinction between two class labels. Margin in support vector machine, to classify a point as a negative or as a positive, we need to define a decision rule. We can define decision rule as, for example, as I told you, that we need a function which is called, like, objective functions, and with the objective function we have some constraints. So this is like, how the objective function and constraint looks like. For that you need to study a little bit operation research subject, which will help you out that how to find these boundaries. If the value of this one, when we can say it's a positive point, otherwise it will be negative point. Now we need a W and B such as the margin. So here has a maximum distance. Let's say the distance is D. So the distance you can see over here, it can increase and decrease, and we can calculate the D. We need an equation L1 and L2 for this. We take few assumption that equation L1 is, for example, W multiplied by X plus P equal to 1, and L2 is W multiplied by X plus P equal to minus 1, right? So these two equations, these will suffice it to find the distance between this one. In order to get our optimization function, there are a few constraints to consider. The constraint is that we will calculate the distance in such a way that no positive or negative points can cross the margin line. Let's write these constraints mathematically. Yeah. So for all the right points, we have it like, this is the function, and for the negative function, which with the minus 1, and for the green points, we have with the plus 1. Or we can say that like every point is to be correctly classified, this condition should always be true. Okay, so this is our objective function basically. Yeah, so usually objective function are equal in size, but if there is some like slack, or like there is like some like extra thing or some minimum thing, so usually we can convert these inequalities to the equality by adding the slack value. Okay, so this is like, more mathematical derivations for this one, for support vector machines. For that one, you need dig deep into that one, and it has been solved like just like by transposition of the equation from the left hand side to the right hand side, and then we got the basic equations, which is equation number 1 at the end. Problem with the SVM. Yeah, what is the problem? What if the decision function is not a linear? Now see, it's not a linear. We have like, the data points in the 4 quadrants, and it's not the matter of positive and negative. Now we have like a 4 quadrants here. Now this, like, if you want a circle, so it's not a linear basically. It's like a non-linear, and the equation will be different. Like, there will be like a square in the equations, right? So a non-linear, then we do some kernel trick and imagine a function phi that maps the data into another space, like, yeah. So then we can have a like, two-dimensional things with a different space, like x-axis and y-axis, and then we can say that how it works. Yeah. So phi function is which is used, and this phi function is equal to r power d, and which is equal, like, which leads to the h, right? And h is can either be like, positive and negative as well. Yeah, so we need to remember a function we want to optimize. Like, for example, if this was we want to optimize it. So as I told you, that in operation research, equations are not meant to be as it is. You can optimize it. You can, like, for a better decision. So there is a cross product, there is a dot product basically, and we have, like, for example, phi xi dot phi xj in the nonlinear case. So if there is a kernel function k such as this one, we do not need to know phi explicitly. Yeah, so because by this way, phi becomes like, meaningless, and you don't need to know about that one. And by this one, you can easily find the kernel with exponential function. Kernel in SVM. So what are the kernel is SVM? You can see over here, like, we have two options here: linear separation and non-linear separation. And then we have a like, 2D separation with the phi, and 3D separations, and we have like, so these kind of, like, separations of the data we have it. And similarly, then we have like a linear kernel, RPF kernel. These are and polynomial kernel and sigmoid kernel. These are the different like function available and the corresponding equations we have it. Finally, the decision boundaries. Yeah. So as I told you that we have these objective functions, and these objective functions can be like easily applied mathematically either in Excel or in any like simulations software. The decision boundary can be found by solving the Pauli constraint optimization problem. So recap of the constraint optimization. Suppose we want to minimize this subject, then necessary condition would be like this one. So this is more like mathematical, and for this one, it's better that you solve it in a paper and pen. That would make you more freedom to play with this kind of equation. But I would just like to elaborate you that what this equation is for, what are these derivative of the function. So here we use the derivative of the x, and we know that we have already learned in our high school what is derivative and how it works, right? Yeah, so this is like more like inequality, that how inequalities work. Yeah, so these are like for inequalities, and example of kernel function. These are like for a polynomial, this function will be used, and for radial, this function will be used for. Yeah, so there are different like for tangent inverse we call it tan h or tangent inverse. Yeah, so this one it doesn't satisfy the Mercer condition on the case. So Mercer is like also one of the algorithm we need to this some condition, and we need to satisfy that one sigmoid with the parameter. So these are like different like variants you can say of the SVM. So value of discrimination function, like, so let's suppose if you have like a class A, class 1 and class 2, and then how we discriminated, how what are the value of discriminant function. So sometimes some function can give you a good example, and it can bypass class 2, and it will also cover your class A in both sides, whether it's in the quadrant of 1 and 2 or 6, or whether class 2 is in the quadrant of 4 and 5. So this is non-linear kernel, okay. Okay, and this one is like some more example. This is what I think seems to be like a medical example with the different cells which are like malignant cell and benign cell. So like blue, let's suppose blue is a like like a benign cell, and red is a malignant cell, or like vice versa. So this is SVM applet. So applet is usually used in the Java and before and now, because people are using more Python. So people might not have the concept of the applet, but it was very popular in the Java. Yeah, so this is the example we have it with exponential. Yeah, so we will stop here, and then in the next session we'll talk about the KNN in the perspective of the SVM.